now?
Yes, I think it's on.
I think it's on. Thanks.
Okay. Welcome to the. So let's continue with the last talk of the morning, and we are very happy to have Pedro, who will tell us about the holographic. Sorry, even though I'm the chair, I am also nervous. So I forgot. So some of us were indoctrinated to be nervous every single time that we are in front of some people. So sorry about that, no, Pedro. It's okay. And he will tell us about holographic refined entropies and Euclidean fluids. Thank you very much.
Thank you. So, okay, welcome everybody. My name is Pedro Jorge Martinez. I work at EFLP in Argentina, in La Plata, funded by CONICET. Today I wanted to talk to you about this project that we did alongside César Aragón and Horacio Cassini. It is it is titled Holographic Refined Renyl Entropies in the limit n to 0 and its connection to Euclidean fluids. So as an index, let me say that I will I will review the refined Renyl entropy prescription to compute it in holography. And then we will review also the known analytic solution, the most famous known analytic solution, which is the hyperbolic black hole. But we will do so in a way that we will make this Euclidean fluid coordinates manifest. And then hopefully you will be convinced enough of the ansatz that we will propose to solve this holographic problem, at least at leading order in n going to 0. So at that point, mostly the things I wanted to tell you will be already over, but I will review some interesting properties that our ansatz has for d bigger than 2 and for d equal than 2, and then we'll hopefully draw some conclusions. So, at least by my count, I think it's fair to say that from the seminal works by Ryu-Takayanagi and Maldaceno-Lukowicz and many people that are sitting here, holography has provided a beautiful geometrical picture for some quantum information measures, and in particular for the problem that we are looking at today. In this work by Dong in 2016, it was proposed that the refined Renyl entropies, which I thank Alice for introducing many of the quantities I'm using today, you don't see gray here. So there should be a manifold here that I don't think you're seeing, but there is a subsystem called A. If we are able to access the reduced Renyl entropy, the reduced density matrix here in row A, one elevates to n, takes trace, log, and performs some operations that require you to know this quantity as an analytic function in n, and I will be thinking will be between 0 and infinity. Then you can compute this quantity, which is called refined Renyl entropy. If you're more familiar with Renyl entropies, as Alice told us, you can get the traditional Renyl entropy from integration on this equation and go back and forth between these informations. So what I'm saying is that the proposal is that you can compute this refined Renyl entropy holographically by looking instead of this other problem. Let me move there. Okay, I don't know. Well, the hand will be there for the rest of the talk. What you can look at is at this alternative problem of gravity coupled to a back-reacting brane. The index n in the computation enters via this tension here, which is n-1 over 4ng. The boundary of the brane is anchored to the boundary of the entangling region, but is otherwise free to move inside the bulk and back react, and generates a conical defect of 2 pi over n. So suppose, okay, I have this gravity problem. It's a nonlinear coupled gravity problem, but suppose I have the solution. The prescription tells me that I can compute the refined Renyl entropy as the area of the cosmic brane that is sitting here inside the bulk, which in general will be a highly non-trivial function in n. So if you were paying attention in my last slide, there was a very bold-faced if, which is that the fact that this problem is highly non-trivial to solve. And actually, I know only of one analytic solution in which I have control over what's going on. So one of the motivations, at least for the talk, perhaps one of the motivations to study this problem is to try to put this to work. You know, just to find at least a simplifying limit in which I can do some analytic computations, try to understand something perhaps beyond the numerical. And this is not a mystery novel. You know, we will be putting this n to 0 here. If you go from 0 to infinity, n at n goes to infinity still yields for me a finite tension. So perhaps that is not a very useful simplifying limit. At n goes to 1, this is the very well-known von Neumann entropy. So n going to 0 is like the natural limit in this context to try to simplify the computation. Taking into account some discussion that that we had last week, and perhaps some talk yesterday by Christian and others, the most natural problem to solve from the CFT point of view, perhaps, is to grab your system, replicate it n times. So in the boundary you have a replicated manifold, which is represented here by this 2 pi n, and the prescription, this alternative prescription also given by Dong in 2016, is to look for vacuum solutions to the pure gravity problem. Assuming the solution we are looking for does not spontaneously break replica symmetry, the point of view we are taking is this alternative point of view in which we quotient this 2 pi n replicated manifold into a 2 pi regular. We have for any n the same boundary metric, but in exchange what we have is that alongside the fixed point of this set n, the set n quotient inside the bulk, what we get is that it is effective codimension to back-reacting brane, giving us this 2 pi over n conical defect. And this is the picture that rises in the bulk. Now we are looking for, not for vacuum solutions, but rather to gravity solutions plus matter. And in the boundary, what we can see is that we will get this like an n-dependent excited state that Alice also told us about in a second. So for the rest of the talk, I will not be discussing this replicated manifold computation, but rather a picture in which we always have an n equal 1 geometry at the boundary, and we are looking for non-vacuum solutions of gravity. Yes, please.
Will you comment at all about this assumption of no replica symmetry breaking?
No, I will not be discussing replica symmetry breaking. We will find a solution that, since our setup already starts with the brane, I would say that our method cannot find solutions that are that break spontaneously symmetry, replica symmetry.
Do you expect that to be a problem in the n to 0 limit?
No, for reasons that have to do with some other projects that independently find similar results as ours. Okay. By Dong in last year. I'll come back to that, but thanks for the question. Okay. Yes, please ask questions. So I will begin now again. Okay, I should use a darker shade of gray. Imagine that there is some square here, which is the manifold. This is a Cauchy slice actually in the manifold. So as I said, we will pay special attention to n to 0. Okay, so here I'm just restating again the tension. This is, and as n goes to 0, this becomes really big. This is just a definition of the modular Hamiltonian. One can always think of these reduced density metrics in any region as an n to the minus n. So the motivation here is to write for you something that looks like already like a thermal state, but a thermal state in a notion of energy given by the modular Hamiltonian. The state that I will be, the interpretation I will give to this reduced density, this refined Renyl entropy is not in terms of this replicated manifold of the CFT in the boundary, but rather as computing, if you grab the definition that I gave and you write it in terms of this new state, you can see that you can alternatively put the problem of refined Renyl entropy in terms of a von Neumann entropy of this state reduced to the density matrix A. And this is the point of view that I will take in this talk, rather than a replicated boundary manifold. And at this point, as I said, this is a thermal state with respect to the notion of energy provided by the modular Hamiltonian, and in the very n to 0 limit, this will be like a high temperature limit. I will also take some results that we get from an earlier work on this entanglement temperatures and very n to 0 limits of this Renyl 0, to say that when n goes to 0, the notions of energy provided by the modular Hamiltonian and the ordinary Hamiltonian are not the same, but are proportional to each other. So I am able to re-understand this high modular temperature in terms of some high energy temperature point by point in the system, and at very high modular temperature, one expects this highly interactive system to achieve local equilibrium and have a good hydrodynamic description. All this to say that this n to 0 limit, effectively this high temperature limit, will allow us to model our system or our subsystem in the CFT as a Euclidean perfect fluid in this very n to 0 limit. And this connects also with some other results that we got for asymptotically free theories, in which a similar approximation is valid, but since for holographic theories, we expect the theory to be strongly coupled even in the high UV, so we don't expect them to be free. So this is where the fluid model emerges. For asymptotically free theories, what we get is a gas of free particles governed by a Boltzmann-like equation, and some statistics also rise. I should say that if you're not entirely convinced by now of this limit yet, this is perhaps also natural, but just wait a second, because we will, like a posteriori, we'll find that this fluid naturally emerges from the gravity equations of motion. So if you are already into this literature that was also used in this paper by Oguri and partners, it's okay, and if not, we will see the fluid emerge itself from the bulk equation of motion in a very naive way of trying to solve the gravity plus brane problem. So to characterize entirely the system and to be more specific, we find the fluid to be a Euclidean conformal relativistic irrotational perfect fluid in flat space in d dimensions. The structure of the T mu nu that we get for our reduced state is of this form. This is G mu nu, the background metric. This is U mu, the Euclidean fluid velocity, in the sense that it squares to +1 instead to -1, if you're familiar with this type of models. And this is beta. Both beta and U are functions of all the boundary coordinates. The entangling surface, this fluid is related to the entangling surface because in this n to 0 limit you have very strong twist operators inserted at the surface, at the entangling surface. So this manifests in the fluid as vortexes that appear in the entangling region. And the thing that one must take care of is for the solution, the boundary conditions for this solution is to be like well defined in the infinity, but also there are these topological properties that have to do with the vorticity of the solution around any form of this entangling surface that one wishes to solve. At this point, well, here there's just the T mu nu is conformal and it solves the equations of motion of fluid, and the only trace of the theory being holographic is captured here in this Stefan Boltzmann constant in front, which is the only trace of Gn that appears here. So I traded you, for the moment, the problem of solving a solution of gravity plus brane in terms of, which is very difficult, into a problem of fluid with vortices, which is also very difficult, but perhaps it can be tackled numerically. So at least, like, I'm more confident that I will be probably able to solve the second problem rather than the first. And at this point, it will be like the first time I will, this is a way to post our result. Our result is that suppose you give me this solution, either numerically or analytically, for this number of vortices. This is in general very nightmarish, because if I have, for example, this system, the fluid, I'm sorry. Here, if I have this system, the fluid solution will also be like very hard, but suppose you can tackle it numerically. You give me that solution, what we have built is an ansatz for the gravity problem, gravity plus brane problem, in the n to 0 limit, that is explicitly written in terms of these Euclidean fluid variables. So you give me your fluid solution, we put it in our ansatz, and that ansatz allow us to compute the area of this brane that we see in this approximate solution. And using gravity as an auxiliary, since the metric already depends naturally on the Euclidean fluid variables, we can rewrite this area of this brane only in terms of the fluid degrees of freedom. In particular, this integral the local temperatures on the fluid. So my main draw of this slide is to say that we have used for these holographic CFTs the property that they can be that we can use the non-prescription to compute, but by the end we just jumped over it, and on the right hand side and on the left hand side we have connected two theories that live in the same number of dimensions. We can model the CFT as a fluid. The fluid has a local velocity. The area of the brane that we are looking for depends on this local temperature, but the last equation is no longer holographic, except again for this Boltzmann number. Since the model that this is just a comment, since the model that we use that we get for the boundary fluid is a perfect fluid, this comes free with an entropy current which is conserved, and if you are looking for something that looks more covariant than my previous result, you can also express this n to 0 limit of this refined Renyl entropy as the flux of this current across something that is either A or anchored to the entangling surface in the boundary. So this is okay. So now I will tell you more or less exactly the same, but with an example.
Question?
Yes, please.
Can you go here?
Yes.
Last slide.
Yes.
Did you say what gamma was?
Gamma is any loop that goes around the entangling surface.
Right, but do you impose any conditions? So
yes, the vorticity. I need my fluids to do this around any loop of this nature.
There.
Yes, I must. Everything must be any integral around this loop, big or small, must give 1. That kind of vortexes are called irrotational, I think. But we can, yes.
Is that a unique choice? Could you do more exotic things?
From the gravity problem, for fluids, for sure. For fluid, there are other type of vortices for general fluids, but for the problem that we will be studying, this is forced to us in order for the gravity solution to have the correct conical deficit. So there is no other choice, at least that I can think of, for the problem. Yes.
How do you calculate the effective temperature of the fluid that goes in the formula? Next slide. Next slide. Yeah. Beta of x. Mm-hmm. How do you compute that?
It is a solution of a perfect fluid, a Euclidean perfect fluid. Like it meets gradient of it meets this equation with this form of T mu nu, and the boundary condition of the solution having going to 0 in the infinity, and then meeting all the adequate vortices fixes you the solution uniquely. So the problem is entire. You can put the problem entirely in the boundary. Thanks. Okay, so now perhaps it would be useful as for the questions to give an example and to see where everything rises from. I will cover again this very simple example of Renyl. The Renyl subsystem. We will map this to a hyperbolic space using a very famous map between the Renyl subsystem and the hyperbolic space at fixed temperature, and we will actually try to solve this brane plus gravity problem for this asymptotic boundary. The virtue of the map is that the entangling surface gets always mapped for any n to the horizon of this Euclidean black hole, so we will be able to have analytic control of the conical deficit and on this fixed point of this zeta n replica quotient for any n. It will just become the mass of the black hole. But we will be able to solve the problem exactly for any n, which is very, very weird. The problem was solved by Myers many years ago. This is the metric that you put, and what you find when you solve the equations of motion is that the black factor here in G only has a single free parameter, which is rho h, that we will need to fix in order to accommodate for the tension. And I make a very stupid comment, but I promise that it is useful. It will be useful later. Is that my system is in ADS, so my system needs to have a cutoff, rho c, and my black hole is mass will be rho h, and this is the domain of rho h. I cannot put, if I'm in a box, I cannot put a black hole bigger than my box in my box. So we'll have to take care, and this will contain interesting physics when we turn this into a fluid. I promise this will come back later. So this is just a check that the metric that I gave to you reproduces this boundary metric in the boundary when we go very, very far away, when rho c goes to infinity. But the most important thing that's going on is that to graph this metric, go close to the brane. This is a very standard. There are many equations here, but the ones that you need to look at are in red, just because if anyone wants the details. This is just the expression of the metric near the brane. And what you get is that to reproduce the correct tension and conical deficit, what we get is that rho h is no longer free, but actually becomes this non-trivial function on n. And with this, one can compute the area of the brane that comes from this piece of the metric, and you get a celebrated result that everybody knows. But two hints that one can have from here is that first, if you expand to n to 0, so now we have an exact solution, and this is an exact result, and then the first thing we will do is to expand this around n equals 0. For n equals 0, this becomes a d, this d cancels this d, and you get essentially the thing that you will know is that the leading order in Sn going to 0 is that this 1 over n to the d minus 1. And this we will try to reproduce with the Ryan sets. Also these finite pieces. So before doing that, what we will try to do is to learn something from the what's going on in the boundary, and we will do so by looking at the stress tensor. The stress tensor can be computed very standardly for any gravity solution that we have. We can either expand in Pfefferman-Graham coordinates or something, but what we get for this example is that the T mu already looks like a perfect fluid. It has some interesting structure here of n-dependent functions, but here it is the temperature of this, the would-be temperature of this fluid, and this u mu velocity. But in a sense, this is a very boring fluid because BH is just a number. Recall that we have fixed the BH temperature, and the UH is also a very boring function. It's just a constant vector. But we can do more interesting things by coming back to the actual problem that was of physical interest to us, which is either the Rindler of the sphere. You can use the map in two ways. And now we do have a beautiful perfect fluid with Euclidean space-time dependent. Well, this ceased to work, but no, I was using it wrong. We have this space-time dependent beta and space-time dependent u in this form that had to do with the Weyl rescaling that we have to do. But the metric now is a flat metric in the boundary. But the most important thing that we learned from this is that the condition, by fixing in the metric the rho hn as we found, we can rephrase the condition for a solution to have the correct conical singularity in terms of this closed integral of th. If we fix th to have this domain, having fixed this beforehand, we can rephrase our condition of the correct conical singularity in terms of this integral. This is sort of a stupid statement, but if we rephrase this in terms of this fluid velocity and fluid temperature, then we can put it in a more covariant way, and then we find that this u mu over beta in this perfect fluid models is the vorticity, actually forms the vorticity tensor, and this condition turns into the one that we will always ask our solution to have the correct conical singularity. Okay, so this is the metric written in terms of this fluid degrees of freedom. This is the blackening factor. I have mapped this into something that looks asymptotically flat. These are the temperature and velocities. This is the vorticity condition, and I will not comment on this. I will come back to this later. But now, by now, like, people have solved the Rindler problem in many ways, but we don't want to depart from the Rindler example and try to see if we can understand something beyond the Rindler example. And what we can do is to expand the metric that we know it's an exact solution to the problem that we're looking for n to 0, now that we have written them, not that we have written it in terms of these fluid variables. And what we get is this. This will be our ansatz. I will show you that it meets the Euclidean, the gravity plus brane solution. There is an interesting thing going on here in the domain of Z. Look, I have chosen to show you, you can use very coordinates, but I have chosen to show you a coordinate in which the brane is sitting at L all the time, and everything interesting is going on in the near the cutoff. I will show you a plot of this, but the statement is that this metric is, of course, no longer an exact solution to the equations of motion, but if I grab this metric still has a conical deficit. The conical deficit is the correct one, and it still looks, there is something that looks like a brane, and the brane, if you compute the area, you exactly reproduce the n to 0 limit of the exact solution. So this is what make us think that we were on the right track. So now is the comment on the cutoff. The first thing to notice here is that there is an epsilon and there is a 1 over n. So this instructs us in this not putting a bigger thing inside your box, is that there is a relevant parametric limit here in which epsilon must be taken, n wants to go to 0, but epsilon, which is the UV cutoff on the CFT, needs to be taken smaller than that. Here's L sitting here. Here is a naive epsilon, for example, constant epsilon limit, but the cutoff actually looks like this, and it looks like this because you have epsilon over n, which is taken to be small, but recall that beta also plays a role, and beta is a function of your space-time. These spikes that you get here can be as slim as you want because you're taking epsilon to 0, but what happens is that near the entangling surface there are some twist operator insertions, essentially. So there is no, and at those points you can always show that beta goes to 0. So what you get is that it is not clear from here, but this has strong consequences on the topology of the solution. For example, for two intervals, what you see is that the solution looks something like this. It doesn't look like a connected solution. It doesn't look like a disconnected solution, but it rather looks like something that is completely connected, like something degenerate happened at n equals 0 that made both the connected and disconnected solutions to become a single object. And we will come back to the question that Stefano made a while ago, and why do we think that this picture makes sense in the n to 0 limit. For the moment, this is just the geometry that has emerged from this n to 0 limit of this exact solution. The statement is that this works for any entangling surface, for any number of regions, and for any topology that you want. The problem that you're putting yourself into is that of computing a very complicated fluid equation, but if you can solve that numerically, then you get the Renyl 0, the refined Renyl 0. Okay, I'll probably skip this. Okay, the comment here is that in the exact solution, there is a very different role played by n and by beta, because the function in n is a highly non-trivial one here, and the function in beta is simply this power. But as n goes to 0, what we see, physics that we see emerge, is that the full structure on the function of n dilutes, and what happens, for example, here in this explicit example, is that rho squared here, this goes as L over n for n going to 0. This thing wins over the 1. You get a 1 over n squared, and we got a 1 over n d to the minus 2, and this comes along with the beta, and it always comes for the right. So the bulk effectively fills a solution of temperature n beta. So beta goes in general is of order 1, but the bulk solution fills n beta, and n is going to 0. So this essentially, it is first also a second way of seeing that there is an effective high temperature limit going on in the system. And importantly, we were able to write this condition in an n-independent way. So this is a topological condition to demand on your fluid, and it does not simplify further. The n-to-0 limit took you all the way to a perfect fluid, but then you actually need to solve the perfect fluid with these strength 1 vortices. There's no more simplifying than that. Okay, this is another comment that we do expect. We try to find subleading corrections to this n-to-0 limit solution, but we couldn't find any in this quite complicated problem. But one can think of that this is a degeneracy. This type of topology is a degeneracy that has appeared at n equals 0, and the first correction already perhaps correct this. For example, can solve this like 4-point function into something that connects in a particular way. So we expect non-trivial corrections to this solution. We couldn't find of any, but we could show that the corrections that to this metric that appear will not modify this leading order Renyl entropy. So perhaps you are interested it is an interesting problem to find these corrections for example, a project similar to the fluid gravity correspondence that people here in the audience have developed. If you are interested in say, oh, okay, what type of fluids appear in this kind of problems, and what type of fluids are holographic or rise on this type of problems, but this is not exactly of interest to us if one looks at the Renyl 0. Okay, so now I will give you what I promised, which is to show you that if you are agnostic of this fluid model, one can look of it rising directly in the bulk. What I'm going to see to start a new problem, which I didn't tell you anything about this, and I will try to, you will still have my ansatz, and I will put them in the equations of motion that rise from here, and we will find the fluid ourselves. So one of the advantages of the answer that we made, that this is looks very similar to a boosted black brane that moves very slowly in this n to beta effective temperature, and there is an analytic map to put it in a Pfefferman-Graham frame. This change of coordinates is not very important, but I put it just if you wanted to see it. But we will see that as n goes to 0, there is an interesting hierarchy of things going on. So the advantage of putting this problem in the Pfefferman-Graham coordinates is that there is a very elegant way of writing the equations of motion for this setup, for this gauge. These are the Einstein-Hilbert equations. And of course, it needs not to say that our answer is not an exact solution of these equations. Otherwise, we will be more happy than we already are. But what does happen, what one can notice, is that by gauge choice, I'm calling this big G, the metric on the bulk, the full bulk, and this mu nu small g with the metric at the boundary. The piece of the metric that corresponds to the boundary has to fit in the boundary. By gauge choice, we put this to be order to have no factors of n. The g d mu, which will be by gauge fixing here, they are 0, but we can consider them in terms of n to be of order 1. But notice that this g mu nu here that appear has a qn squared, and qn has a 1 over n. So these pieces of the metric do have a 1 over n squared, so they are highly enhanced. 10 minutes, great. So what one can see if one toys around with these equations, whether they simplify in an n to 0 limit, you can see, for example, this equation. This has a g minus 1g, so the n factor cancels. This is g minus 1g, g minus 1g, so the n factor cancels again. So both of these are of the same order, and we must diligently solve for them. But in these terms above, for example, you have g and also g minus 1g, g. So this is of order 1 over n squared, 1 over n squared. But Ricci G, you have a reminder here of the definition, is actually of order n to 0. So this term is the only one in this whole structure of terms that simplifies. And what happens is that our answer is a solution of this system where the Ricci G term is disregarded. More interestingly, the form of the ansatz makes that for any choice of beta and mu, this tensorial solution, this tensorial equation, sorry, is 0. The scalar equation is also 0, but in the vectorial equation, if you put it here, you get exactly this equation, that is exactly the gradient of mu, the equations of motion of a perfect fluid. the condition of the brane. Of course, that's not right here because it only puts delta boundary conditions on your gravity problem. So you are not able to see the brane here. You need to impose it a posteriori, and it rises. It turns into these vorticity conditions for the solution of the fields. But it's not something that you can look at locally because it imposes it puts like a delta on the matter side of the equations. I will not be able to cover this. Okay. I think we are doing fine, in time-wise at least. Okay, so that is the story that I wanted to tell you for d bigger than 2. Our solution is approximate. We already know that it is not a good solution exactly. We can correct it, but it is good enough to compute the Renyl zero. A slightly different story appears in d equal 2, and it is something that I'm working on, so perhaps I can tell you a story about it. You grab our ansatz, you evaluate for d equal 2, and you put it in your equations of motion. Surprisingly, you would expect it not to be a solution, but it actually is. Of course, the beta and mu must obey the fluid equations of motion in 2 dimensions, but in 2 dimensions, these very complicated fluid equations of motion turn into a Laplacian. But the Laplacian you can solve. The most complicated system that you can think of in CFT2s are any number of intervals, but I can solve the Laplacian for any number of intervals, so the solution, you get a solution, it doesn't matter very much how is it, but now we have a candidate, the keyword is candidate, exact solution for the problem that we are looking for that spits to you an analytic expression for the Renyl entropy, refined Renyl entropy as a function of n, as an analytic function of n, and it is very, very simple. But of course, this is too good to be true. So in order to understand what's going on here, what we look at is, so the bottom line is that this is still an approximate solution, and I will tell you how. But since in ADS3, all the solutions are locally ADS3, and we are trying to fix some very delicate delta properties of our solution, we need to look at some topological properties. The easiest way to see that we are not actually solving the problem that we wanted to solve is to compute the induced T mu nu in the CFT. The induced T mu nu in the CFT has a leading 1/n term. This both T mu nu and F mu nu. Its form it's not very important, but they are both of order n to the 1. It does not have powers of n. This T mu nu is the perfect fluid with the exact twist operator insertions that you would like your T mu nu to have. For example, in this two interval scenario, you have a twist operator here, one here, and one here, and one here, and all these all these insertions are in this object. And this 1/n squared fixes for you the correct conformal dimension of the twist operator for the problem you're looking for. But there appears a new term, which is of order n to 1, that appears exactly because you're solving for a perfect fluid. Because you're solving for a perfect fluid, the fluid equation force trying to manage all the vorticities at the same time, the solution finds itself into a sort of for any intervals 2n minus 2. In this case, it's just 2 extra points at which the velocity cannot solve itself. You get a 0 velocity points, and this induces points in which the temperature goes to infinity. The fluid temperature goes effectively to infinity, and this extra divergence that we were not looking for appear here and appear as extra insertions of operators that we don't know what they are. So we thought we solved for fluid. We put in our ansatz something, but the CFT that it's induced in the boundary by this solution is not the T mu nu that we wanted to find. So this is the way in which ADS3 captures the fact that this solution is still not exact. It has not the good T mu nu at the boundary that we need. Of course, as n goes to 0, we do recover the result, and actually this is the right solution in the n to 0 limit. Okay, so this is exactly what I said. There are some topological obstructions of understanding this as an exact solution, and if someone is have already read, I think I have 5 minutes. Very good. Okay, one last comment. By now you think, oh, okay, you have a boundary metric that you want to fix, and you have a T mu nu that you want to fix in a 2-dimensional solution. why not you use Bañado's solution, right? It is written in terms of, it is in particular written in this form, but it's explicitly written in terms of the T mu nu. So perhaps if you already know what T mu nu to put, okay, put it and then look for the brane in that is an exact solution that has the correct T mu nu that you're looking for. The T mu nu, we can compute it for a perfect fluid here in this very simple form. But this method also fails because life is not easy always. What happens is that generically when you look for the Bañado's type of solutions, but the T mu nu that you put has boundary insertions, like we always do because we have entangling surfaces, you can see that the coordinates break down from the boundary up to the interior. They break down, and they actually break down at the codimension 1 surface. And the change of variables that would allow you to go beyond that are quite non-trivial. This similar problem was studied by Pedro Vieira and collaborators for a different type of problem. But the fact is that this method gives you an exact solution with a good T mu nu, but does not allow it. It is yet mysterious how to get to the brane. What one can show is that as n goes to 0, this codimension 1 surface that you find that obstructs you from getting to the good conical deficit to the brane solution degenerates into a codimension 2 object, and you once again fall into this type of geometries that we were describing before. And this solution from the Bañado's limit also match our ansatz. I will skip this because I will not have time, sorry. So now to Stefano's question. Generically, what one hopes, for example, looking at the von Neumann entropy, is for example, for the case of two intervals, to have a solution that has a standard topology, perhaps a connected or disconnected region. But in December 2023, and actually 1 year later by Pennington and Rath, they don't explore himself his prescription again for n less than 1. And at first it found some quite trivial corrections, but something funny happened. He expanded the reduced density matrix in a fixed area. It is a completely different approach as ours. He expanded the the reduced density matrix in a fixed area expansion, taking some hypothesis that I do not quite follow, but what he conjectured in that work, and Pennington also found similar results, there should be, for a finite n, but below some model-dependent finite number of n, that the correct saddle is no longer nor the connected nor the disconnected one, but a phase in which both branes coexist. So it doesn't have this structure does not have a trivial connected or disconnected nature. These no longer have the same. These have generically different tensions, but they do have the same area. They find that the saddles that dominate both branes exist in some sense, but both have the same area, and they call these diagonal saddles, extra diagonal saddles that appear in the n to 0 limit. Our conjecture, as our JHEP referee instructed us strongly to say that this is a conjecture, what we think is going on here is that this type of saddles become appear whenever you are below certain n threshold, but then the tension becomes, you should think of this negative tension of someone pulling very, very strongly from the bulk outside, but also the branes very highly interacting between each other. So what we picture is that in this n to 0 limit, what happens is that this volume start to shrink because the branes become very, very attracted to each other, and in the strict n to 0 limit, this solution degenerates into a single point, and you get like a fully connected object. No problem. I will skip this. This is sad because this is a generalization of some result by Christian here. So as a conclusions, we found the n to 0 leading order solution for the holographic Renyl entropy problem as setting down. Naively, we were not looking for it, but naively we got to to some solutions that are in touch with recent work by Dong on his own prescription and some corrections that rose from it. We model the CFT. There is a CFT model, an Euclidean perfect fluid for the boundary CFT emerges in the gravity equations. We expect corrections to change drastically the topology. Those are interesting to look for. I did not mention this, but this expression of Renyl-0 entropy, depending on some sort of emergent temperature of the system, appears to be highly universal. We have shown a similar expression holds for asymptotically free theories. And okay, this I already said. So thank you very much.
Thank you very much, Pedro. We may have time for one or two short questions, unless you guys are very, very hungry. No?
So you drew this interesting diagram for n equals 0 with your new phase. But I would think that this kind of fluid gravity approximation would allow you to say what happens to first order for n not 0 as well. And so if you allow n to be perturbatively small, what happens to this degenerate structure?
No, I don't know. No, I don't know. We tried for if I understand your correction, your question correctly, we tried for a couple of months to see if we could correct our ansatz. In the standard fluid gravity correspondence, you do have it's not an absolute. Step by step, if you're diligent enough, you could build exactly the fluid that lives in the boundary. You go to first order, you go to second order, and so there is a method to correct your solution. But this fails. This is a slide that I couldn't show. This Euclidean manifold in that the fluid gravity, there was an importance of choosing some light-like coordinates that help you to disentangle the problem and find this method of correcting your answer. Here we are in Euclidean in a very different set of equations, and at least we weren't smart enough to reproduce this method to correcting. So what I can do for the moment is to go in that direction, drawing from, and with some intuition and drawing from the results of Dong, but I'm not brave enough to tell you what's going on whenever n is smaller.
And can you remind me from the Dong results, when you say that both branes are present, is that because he found some replica symmetry breaking, or is there some sense in which replica symmetry is preserved and yet both branes are present?
The arguments made by Dong are based on like in a fixed area quantum mechanic approach expansion, and then he uncovers this type of phases doing like a Gaussian distribution model of this density of states. So how did he trust enough that intuition to find these new phases? I wouldn't have been brave enough, but I'm not also, I'm inclined to tell you that this is not, if there is a way of a replica symmetry breaking argument for these solutions to appear, I would say it would be weird, if that's going on, I would say that it would be weird for us to find these solutions, because we are explicitly under the hypothesis that we are looking for non-replica symmetry breaking, because we are in the brane setup.
Except that it looks like, in some sense, that might go, the breaking might actually go away at n equals 0, because both of the phases. So I had thought that, I can't remember, I may be getting the wrong paper, but I had thought this was like G's other work that finds replica symmetry breaking, and in this case, in some sense, the replicas, roughly speaking, alternated between the two phases as sort of an entropic effect. But if indeed, as n equals 0, they both pinch off, it looks like the same thing, there would be some sense in which the symmetry is restored at n equals 0, and then you could find it.
Yes, from a different perspective, that would say that I could not correct my solution.
It would be hard.
It will be hard. It will be hard. But in principle, like these are very hard solutions, but I expect for them to have a solution. So at least I expect for it to be a picture I could draw of the corrected solution.
Well, I mean, if my memory of G's thing is right, which it might be the wrong paper, then it's only kind of a Z2 replica symmetry breaking. Every other replica, there's a.
I agree.
In which case, you could imagine that you could find it by doing a double cover.
Okay, I'm looking, if you want, we can discuss. I'm trying to look for an exact solution and I think I'm on the right track, but everybody thinks always that they are on the right track. But I'm looking for an exact solution in ADS3, and I think I'm on the right track. So if you're interested, we can discuss.
Okay.
Thanks.
Any further questions? If not, let's thank Pedro for a nice talk. Thanks. And we reconvene after lunch at 2 p.m.